You interact with artificial intelligence every single day.
Oh, constantly.
Whether you're typing a question into a search engine, unlocking your phone with your face, or, asking a voice assistant for the weather,
Right.
AI isn't some futuristic concept anymore. It's just how the world runs. But how did we actually get here?
A great question.
Our mission today is to trace the deep, winding history of the thinking machine and show that this idea is centuries older than the computer itself.
That's the fascinating part, isn't it? This isn't a story that just starts in the 1940s. The dream of non-human intelligence goes way back.
To ancient times, even.
Yeah, we have myths and legends about automatons, mechanical servants crafted out of bronze or clay, performing tasks for their creators.
So the desire to have something else do our work and our thinking has been around forever.
It seems to be a core human impulse.
And that impulse started to get, well, mathematical in the 17th century. It moved from myth into philosophy with thinkers like Gottfried Wilhelm Leibniz. He proposed something truly radical.
Radical is the word for it. Leibniz imagined that if we could translate all human thought, all reasoning, into a series of standardized symbols.
A kind of universal language of logic.
Exactly. Then all logical disputes could be resolved by pure calculation.
Right. So instead of debating philosophy, you could just say, let us calculate this problem. He actually envisioned a machine that could do it.
He was dreaming of the first logic engine. Now, he didn't build a machine that could solve philosophical arguments, but he and others did build early mechanical calculators.
And that was a huge mental breakthrough.
A crucial one. It proved that a non-living mechanical object could successfully handle what were seen as high-level mental tasks.
But those early machines, while brilliant, were physically limited. They were bound by their metal gears.
Totally. If you wanted the machine to do a new type of calculation, you had to physically re-engineer the object. True, flexible intelligence needed a completely new way of thinking.
And that brings us to the mid-20th century and the person often called the father of computer science, Alan Turing.
Right. Turing wasn't just interested in building better calculators. He was uh, obsessed with the theoretical limits of what a machine could think.
He looked at it from a pure logic perspective. He came up with this idea of a universal machine, a theoretical computer that could simulate any other computer.
As long as it was given the right set of instructions, he basically created the conceptual blueprint for modern software.
And this leads directly to his famous test, the Turing test.
Yeah, and people often focus too much on the mechanics of it. The whole setup, where a person talks to two unseen participants, one human, one machine.
But the real genius is the question it asks.
Exactly. It's asking, does intelligence require understanding? Or does it only require the ability to simulate understanding so well that you can't tell the difference?
So if the machine can fool the human interrogator into believing it's another person, Turing argued, then for all practical purposes, we should consider it intelligent.
It shifts the burden of proof from what's happening inside its head to its external behavior. And you have to remember, Turing wasn't just working in theory.
No, his practical work was instrumental in breaking the German Enigma codes during World War II.
And those early computers he helped develop proved that by following a series of very simple instructions, a machine could tackle a problem of unimaginable logical complexity.
A problem that took human ingenuity to create, but could be solved by machine calculation.
And that real-world proof really paved the way for the official launch of the field.
Okay, so let's jump ahead to 1956 and the famous Dartmouth workshop.
This is the moment. This summer workshop was where the term artificial intelligence was formally coined. It gave this whole new field a name, a banner to rally under.
And the atmosphere was electric. That might even be an understatement.
Oh, completely. The researchers there were incredibly optimistic. They believed that because the human mind could be described logically, they could describe every aspect of intelligence.
Learning, reasoning, creativity.
All of it. They thought they could program a machine to replicate it within a generation. They genuinely thought human smart machines were just decades away.
Their first successes were in really well-defined areas, right? Like math or games.
Exactly. It allowed them to show the immediate power of their programs. They created things like Logic Theorist.
Which could prove sophisticated mathematical theorems, sometimes better than university students. That must have been a huge sign that computers could handle abstract reasoning.
It was. And then there was ELIZA.
Ah, the therapist program.
Right. It was designed to simulate a psychotherapist, mostly by taking what a user typed and just rephrasing it as a question.
So if you typed, "I feel sad today," Eliza might reply, "Why do you feel sad today?"
Pretty much. And what's astounding is how many users, Even experienced computer scientists felt deeply connected to it,
They really thought they were talking to someone who understood them.
sometimes sharing incredibly personal information. It brings us right back to the Turing test core question.
Right. ELIZA showed that you could simulate understanding without having any internal knowledge at all. It was just manipulating symbols.
It was a sophisticated parrot. It was performing the ritual of conversation, but not actually thinking.
But the public hype, the government funding, it was all based on the idea that they had solved the problem, when really they had only solved the simulation problem.
And that mismatch led to a very painful collision with reality.
The first AI winter.
Yes, in the mid-1970s. The euphoria just vanished because the early promises simply didn't materialize, and it was mostly because of physical limitations.
Talk about that hardware bottleneck. Why couldn't they deliver on that promise of general intelligence?
The problem was twofold: memory and speed. To handle the messy, ambiguous information of the real world, all of the common sense stuff that humans just know, you need an unimaginable amount of stored knowledge.
And the computers back then just couldn't handle it.
Not even close. They were way too slow and too expensive to have the processing power or memory needed.
So the government agencies that had been pouring money into this high-risk research started pulling back.
When the funding stops, progress stalls. Researchers left the field, skepticism grew, and the whole narrative became, okay, machines are good at math, but they'll never handle the real world. It was a really dark period for AI.
But the field didn't die completely. It had a sort of rebirth in the 1980s, but they had to lower their expectations.
Drastically. They stopped aiming for general human intelligence and started focusing on extremely specific tasks.
This was the era of expert systems.
Exactly. The concept was simple. Instead of making a machine know everything, let's make it know one thing exceptionally well, using rules provided by human experts.
So you'd feed the system tens of thousands of if-then rules. If the patient has a high temperature and a rash, then the probable diagnosis is X.
Yes. And these systems became really successful commercially. This was the first time AI saved businesses serious money.
What were they used for?
Medical diagnosis, deciding on bank loan eligibility, configuring complex manufacturing parts. It proved that narrow, rule-based machine intelligence could be incredibly useful.
Even if it wasn't, sentient.
Right. But that rigidity, the very thing that made them useful, also became their undoing.
Which leads us directly into the second AI winter in the late 1980s.
The core issue was maintenance and scale. Because every single rule had to be manually entered and tested by human experts, the systems were extremely expensive to build and even more to maintain.
So what happened if the real world changed? Like a new tax law for the bank loan system?
The entire delicately balanced pyramid of rules would often just break down. It required massive human intervention to fix.
They were too brittle.
Exactly. Expert systems required a static, perfectly defined world, and the real world is anything but. So companies realized the cost and rigidity weren't worth it.
And the funding vanished again.
Vanished again. Specialized AI companies went bust, and the field faced another collapse of confidence.
Okay, so we've had two major crashes. First, the hardware was too weak. Second, the rule-based approach was too rigid. So how did we finally escape that cycle and get to the powerful AI of today?
The escape was driven by two simultaneous colossal game changers in the 1990s and 2000s.
What were they?
Moore's Law, which made computers exponentially faster and cheaper, and the internet.
Which provided the fuel.
Fuel in the form of massive amounts of data. Big data.
Think about it. Billions of words, photos, videos, interactions, all suddenly available online. Before that, researchers were stuck with tiny data sets they had to type in by hand.
And this shift was absolutely revolutionary. Instead of relying on a human to write 10,000 if-then rules to identify a cat.
You could just show the computer 10 million examples of cats and let it figure out the rules for itself.
Precisely. The reliance moved from human programming to machine learning.
And this is where an old idea, neural networks, which had been around since the 50s, finally became practical.
Right. A neural network is a mathematical structure loosely inspired by the brain. It has layers of interconnected nodes, and when you feed it training data, the system adjusts the strength of those connections.
So the machine literally teaches itself. You show it thousands of labeled cat photos, and it doesn't get a rule like cat pointy ears. It just learns a pattern.
It assigns a specific pattern of connection strengths that, when activated, correctly identifies the object as a cat. It's all about calculating probability based on the examples it's seen.
So it's more flexible. It's not a hard and fast rule. It's 98% probability this is a cat.
Infinitely more flexible and powerful than the old brittle systems.
And the ultimate proof that this data-centric approach had finally cracked the complexity problem came in 1997.
That was the year IBM's Deep Blue defeated the world chess champion Garry Kasparov. Chess was the perfect test case. It was seen as requiring true human intuition and creativity.
And what Deep Blue proved was that while intuition is great,
Raw calculation deployed on a massive scale could be even better. It was brute forcing the problem, analyzing millions of moves every second.
it could see farther into the future of the game than any human possibly could.
Calculation beat intuition.
And that success was repeated later in even more complex games like Go and poker. It showed these data-driven systems could handle abstract planning on a superhuman level.
Which brings us to today, where these systems are so powerful and so common that you barely even notice them.
Right. Think of the algorithms powering your search engine, deciding which of the billions of results are the most relevant for you. That's intelligent prioritization.
Or when you talk to your smartphone. Complex neural networks are translating sound waves into language, understanding the context, and generating a fluent response.
Even the systems that recommend products or decide which social media posts to show you.
All of them are powerful AI systems trained on trillions of user interactions, and now it's integrated into critical infrastructure.
From car systems that help you stay in your lane to complex systems used in finance and drug discovery.
So what's fascinating here is that the history of AI isn't a straight line of progress. It's a cyclical story of intense dreams, followed by painful disillusionment.
And then breakthroughs driven by fundamental changes in technology.
Exa-
We are definitely living in one of the most exciting periods of intense discovery. But even these modern systems still have their limits, right? They can struggle with new situations or pick up biases from the data they were fed.
For sure. The focus today has shifted. It's less about can we build these systems and more about how we make sure they are reliable, transparent, and fair.
So they can actually help doctors find cures faster or help scientists model climate change.
That's the goal.
We've seen these cycles where the excitement collapsed because the promise exceeded the reality. As AI becomes integrated into every part of our lives, maybe the most important question for you to consider isn't can machines think, but what is worth automating and what must remain profoundly human.
Good luck with your studies.